Assalamualaikum warahmatullahi wabarakatuh. My name is Azif Khan bin Azim Khan. My matrix number is 205537. I am from Team 2, and today we will be presenting about assignment 2, which is the application and principle of partial differential equation. So let me just give you a brief introduction about all the type of equation we have here. The first one is a wave equation, which is a crucial second order linear partial differential equation for the description of mechanical waves and light waves as they arise in classical physics. It can be found in acoustics, electromagnetics, and fluid dynamics. Next, we have the heat equation. So the heat equation solutions are sometimes referred to as caloric functions. Joseph Fourier established the heat equation theory in 1822 to represent how a quantity like heat diffuses through a specific phase. Next, we have the Laplace transform. The Laplace transform is to transform ordinary differential equations into algebraic equations, which makes it easier to solve. Okay, now moving on to the topic, applications and principle of partial differential equation. So the first one is the wave equation. So the wave equation basically studies the behavior of waves in space and time. The simplest wave is especially one-dimensional sine wave with an amplitude that varies, which can be seen from figure 1. The wave function is as follows: y equals to a sine kx minus omega t. So the a here represents the maximum amplitude, k is the wave number, x is the space coordinate, and omega is the angular frequency. Next, to get the wave equation, we have to perform the second order partial derivative on the equation on the function previously shown. So differentiating the wave equation with respect to x gives us the equation 2 and 3 here. Next, differentiating it with respect to t gives us equation 4 and 5. Next, by multiplying equation 5 by k squared over omega squared and equating equation 3 and 5 will give us equation 6, which is this one here. This equation can be further simplified by substituting k, where k equals to 2 pi over lambda, and omega equals to 2 pi f, where f is the frequency and lambda is the wavelength. This will give us the one-dimensional wave equation, this one here. So equation 8 is an example of a three-dimensional wave equation. So this is some applications of the wave equation. As you can see here, wave equations can be seen in numerous applications such as water waves, sound waves, and seismic waves or light waves. So you all have heard of the other waves. So let me just explain about the seismic wave here. The seismic waves are waves of energy that travels through Earth's layers that is produced by earthquakes, volcanic eruptions, and many more, such as the magma movement. And that is all from me. Thank you.
Assalamualaikum Dr. Amzari. My name is Ahmad Miraki bin Ahmad Jasrul. My matrix number is 207449. For the second assignment, I will be covering the heat equation principle and application. First thing first, we have this equation above. Shows that we usually use the formula to explain the condition that heat flows from hot to cold area, since we all know that hot area have more energy to move compared to cold area. I mean hot atoms. But in order to use this formula, it can be only used with the condition the temperature was balanced between both hot and cold area. The equation below was fully derived with the total amount Qt of heat within region V. So now let's take a look at this thin bar right here. We will look at the one-dimensional variant in the context of heat flow down a thin bar. The bar is supposed to have a homogeneous cross-sectional area and an insulated outside surface that allows no heat to escape. The Fourier law equation below states that heat transferred across unit area is proportional to the temperature gradient. where K is the thermal conductivity and the minus sign shows that the flow goes from hot to cold. Moving on to the next slide. Now, this equation is actually from Fick's second law, which applied to the whole length of the bar. The Fourier law before was substituted with Fick's law, which states that a material's diffusional flow is proportional to its concentration gradient. Now, in this topic, there will be two methods of heat equation. The first one is separation method, and the second one is Laplace transform method. Usually, we use separation method when we deal with a linear homogeneous partial differential equation with linear homogeneous boundary conditions. It relies upon assumption that a function of the form with this equation below, which is called solution, and the boundary conditions. There are also linear will be provided and homogeneous which also satisfy the boundary conditions. On the other hand, the Laplace transforms method is quite simple. It often known as equation down below. This equation, Laplace transform is an alternate solution approach for the heat conduction or diffusion problem since it has advantage to deal with boundary conditions, but it suffers from the normal difficulties of executing the final inversion. Now, previously I covered the principle of heat equation and now the application. So surprisingly, it was used in processing image. So mathematical convolution is a crucial tool in describing the sampling process, which the convolution f times g of two integrable functions f, g was defined as below. This one, convolution is a commutative operator like f times g equals to g times f. Let's imagine if f and g are two-dimensional images. Convolution can be defined as this equation. Moving on to the next slide. To get more in detail about the convolution, we will work out a one-dimensional example. F supposedly some signal. For example, this graph. Meanwhile, for gx, we can define it by this diagram. The convolution of this example equals to the equation below, this one. So the effect of convolution is that f gets smoother and clean, small, which means like small details of f vanish. Therefore, in this graph, we can see the flow of smoothness from left to right. So just like the image processing. As conclusion, the larger the sigma value we choose, the more details of f vanish. So let's see the next slide. And this is the example of image processing. This is the before and this is the after. It seems like the before is quite hard. You can see a tiny bit of dot and it is rough, and after it looks so smooth, just like the picture. You can compare it the before and after and you can see it. So that's all from me. Thank you.
Assalamualaikum warahmatullahi wabarakatuh. My name is Muhammad Iman bin Ahmad, matrix number 205901, and I will be explaining the Laplace equation and also the application of Laplace equation. So basically, Laplace equation is to convert one function into another function, for example, an input, a function of ft, to be converted into a function of fs. For the Laplace equation to be defined, the integral must be converged. For many functions, ft is restricted. For example, if ft approaches to non-zero number, t equals to negative infinity, then the integral must be converged only if s is bigger than 0. So this is an example, ft equals to 1. When ft is equals to 1, and under here is, if we solve this equation, we can get 1 over s. So 1 over s here is the function of fs. So Laplace transform of the exponential function. So ft equals to exponential at. So if you solve the equation, we can get the function of fs equals to 1 over s minus a. And the next one, application of theorem hyperbolic function. So if the function is using cos omega t, then we can get s over s squared plus omega squared. And if it's sine omega t, and we will get omega over s squared plus omega squared. So this is the how the integral can be solved, and we will get the answer. So this is some of example. If ft equals to 1, t squared, t power of anything, t power of a, and a must be positive, and so on. So this is what will from ft, and it will be converged into Laplace equation. So now, application of Laplace transform for element in electric circuit. For resistor, for example, for the first example is resistor. According to Ohm's law, the electric current is proportional to voltage and inversely proportional to resistance. So V equals to IR. For resistor, the voltage current relationship is in the time domain t. So Vt equals to It times R. Applying Laplace transform, and we still get Vs equals to Is times R. This shows the resistor does not change whether in time and Laplace domain. The resistor remains the same. For capacitor, the current in the circuit is given. For example, here It equals to capacitor differentiate V voltage in terms of T over time. And by applying Laplace transform, we will get the current is V over 1 over S C minus C V O negative. For conclusion, at the end of this report, we can conclude all the principle and application of partial differentiation. We have explained the detail of wave equation, heat equation, and Laplace transform. The understanding of each principle is important, that the method of application can be applied to any mathematical problem in order to solve them. Thank you.